Alrighty, so explosions and momentum. Common examples of the conservation of momentum center around two or more objects colliding in the absence of external forces. Another twist on the example of a collision would be the idea of a reverse collision or an explosion. If you videotape, or like, videotape's kind of a dated term now, I guess. If you video an explosion and play it backwards, it looks like a collision. Likewise, if you tape a collision and play it backwards, it resembles an explosion. So they are very much related. If we look at the case of a cannon being fired, we find there is a force of gunpowder exploding, creating a force of the cannon pushing on the cannonball, and the cannonball pushing back on the gun. These two forces are equal in size but opposite in direction. Why is that? Newton's second law, right? Equal and opposite. No, third law, right? For every action force, there's an equal and opposite reaction force. If any forces that are external to the cannonball system, such as weight and friction, are removed, momentum must be conserved. Again, that's the key idea. Momentum must be conserved. In the example at the left, the external forces have been removed by placing the cannon on a frictionless surface. In the beginning, both the cannon and the ball are at rest. As a result, the total momentum before the explosion is 0. Right? So you can see, obviously, you don't have the little animation on your paper. That'd be kind of cool if you did. But if you watch mine up here, you see that the initial momentum is 0. What's this funny looking symbol? Anyone know? It is total. It's the Greek letter epsilon, or sorry, Greek letter sigma, and it means add them all up. That's capital sigma. Do you know what lowercase sigma looks like, Mustafa? I'm going to throw you a curveball. Lowercase sigma? Oh, it's been so long. It means something in stats, too. In stats. Stats. Yeah, I'm trying to think of an English letter that's equivalent. No? Fair enough. You did that. I never noticed that before. I'll find one for you. We're going to be here all day. Q? I don't think we're going to be able to satisfy him. Okay. Mathematically, this explosion will look like. So here we have sigma p. You don't need to draw the sigma all the time. It just means the sum of all the momentum or total momentum. I'm good with just pi is equal to pf. Here they've got sigma p is equal to sigma p prime. Remember, the prime means after the event happens, after the collision, after the explosion. So in this case here, we've got a 100 kilogram cannon. It's moving at 0 meters per second to begin with. 5 kilogram cannonball. It's also moving at 0 meters per second to begin with. So the total on the left-hand side is 0. And so the cannon itself moves at -2 backwards. The recoil is -2. The cannonball, it moves at 40 meters per second. And the two momentums are equal and opposite. And the 0 is conserved. The momentum is conserved. Okay? We're going to do a sample where I would ask you to find one of those two things, right? Find how fast one of the two things is moving. You'll notice that the cannon has a new velocity that is in the opposite direction of the velocity of the cannonball. Remember, momentum is conserved, not velocity. So the mass of the cannonball is 20 times smaller than the mass of the cannon. As a result, the velocity of the cannonball is 20 times larger. Consider what would happen if you had a cannon with a small mass and a ball with a large mass. Well, the cannon itself would go flying backwards, right? This concept of momentum being conserved in an explosion is true for an explosion along a line, one-dimensional as in the animation. An explosion along a plane, two-dimensional, or an explosion in free space, 3 dimensions for something like a hand grenade. When you toss a hand grenade, not that any of you would, and it would explode, all of the little bits and pieces, right? All that momentum is conserved. I think we have an example next. Do you guys have this example on yours too? Okay, so let's do this one here. Suppose in the example, the 5 kilogram cannonball moves with a speed of 25 meters per second after explosion. How fast will the 100 kilogram cannon move backwards? So we're going to start. Do you guys have a lot of space to write? Yeah, you do. Looks like. Good. Excellent. We're going to start with PI is equal to PF. Pretty much, because momentum is conserved, right? And then you just have to fill in P initial, yeah, initial momentum, final momentum. And you just have to fill in what makes up the initial momentum. So in this case here, we've got a cannonball and a cannon. So how about we use C and B, I guess, right, instead of A and B. So we're going to have, now what is the initial momentum? I could write out MCV, it's 0. Don't bother, write it out. It's 0. The initial momentum is 0. No. What if it's not mentioned? If the cannon was in motion, like let's say it was, on a train and the train was traveling down a track, and then it shot, right? It would have some sort of momentum to begin with. Yeah. Okay, so the final momentum is, what's that? I don't know. That'd be cool. Train-mounted cannon. You'd have to know all about, relative motion when you're firing it, though, wouldn't you? Just let her back. Now, in this case, I put the little prime symbol up there, but in this case, because the left-hand side is 0, you're not going to have anything on the left-hand side. You can probably ignore it. That prime is just there for us to recognize that that velocity refers to the velocity after the explosion. Fancy. Okay, so we got mass of ball, velocity of ball, prime. The prime means after the explosion, plus mass of cannon, velocity of cannon, prime. Again, prime just means after the collision. It's just a way of denoting, because you could, Billy, you could have, we did this the other day, you could have a velocity of the ball before, right? And if they aren't written differently, then you don't know which one is which. Or you might combine them together accidentally, which would be bad. Okay, so fill in our numbers. Mass of the cannonball is 5. And it moves with a speed of 25 meters per second. The mass of the cannon is 100. And we are looking for how fast does the cannon move backwards. So really, once you got this set up, the math is, as is always most physics problems, the math is pretty easy. Right? It's the setup that's the hard part, right? I don't think so. I can't think of any that come off the top of my head. There is two-dimensional, though, so there's going to be some vector components. So we're going to put 5 times 25 plus 100 VC prime. Solve for VC prime. Minus 125. Divide by 100. And you'd get right? 25 goes to the 125 goes to the left side, Mustafa, right? Why does it? And it has to be negative because the cannon is going to the left and the cannonball is going to the right, right? Those velocities are always going to be what? Opposite to each other. There's really not a whole lot more I can put in here. To make it any harder, I guess I could have it in 3 pieces exploding, but pretty tough to do that in 1 dimension. So there's not a lot to these really. Okay, so you've now looked at elastic collisions, inelastic collisions, and 1D explosions. So I'm going to give you some time to work. I think I've got some handouts for you. You guys have this one here that I gave you. We were kind of tied up right to the very end, but you've got these 3 questions here that you can work on. I wrote the answers on the board there, so some of you that weren't here will need this and need to get the answers. And I've got some more, and I got a whole bunch of stuff to hand out as well. There's also a little hand-in that you were supposed to do as well. That is all for today. From me.